so this video is going to be the first one dealing with Chapter 28. And Chapter 28 is about the sources of magnetic fields, or what causes magnetic fields. Let's see, our first section, 28-1, talks about the magnetic field due to a long, straight wire. Well, if you do experiments, they find two things, both of which makes a lot of sense, and that is that it is directly proportional to the current. We would expect that as we increase the current, the magnetic field around a wire would increase, but it's inversely disproportional to the distance away, and that also makes sense. We would expect this to get weaker the farther away from that wire we get. Turns out that the constant of proportionality is mu naught over 2 pi. So we end up getting that this is equal to mu naught I over 2 pi r. Now, this permeability of free space, which is a fancy word of saying of a vacuum, is represented by the symbol mu naught, and it's equal to 4 pi times 10 to the negative 7. The units are Tesla times meters per amp. Just like we had the constant permittivity of free space when we did electric fields at epsilon naught, we're going to find this mu naught shows up a lot when we're talking about magnetic fields. Okay, so our first formula for how strong a magnetic field is this. Okay, and we've actually already talked about the right-hand rule, that if the current is going like that, we would grab it, and we can picture how those magnetic field lines would be. That's the current. I grab that wire like that. You can tell that those magnetic field lines are going to look like this. Okay. So we know that one source of a magnetic field is a long, straight wire. Let's look at an example now that we've got a formula. This is example, it's in your book, it's example 28-1. And in it says that we have an electric current I, which is equal to 25 amps, and it's vertically upward. And it asks us to find the magnetic field, which is B, at a point that's 10 centimeters due north of the wire. Okay, so we can picture a piece of wire that's just being held straight up like this. Let's just assume for this example that we happen to know that this direction is north, in the north, south, east, west world, in which case they tell us that we want to find it at a point P that's located 10 centimeters to the north from this wire. There's our point. Okay. If we were to look at this from above, we could do that. We could draw it where the wire coming straight out looks like this, pointing straight up, and then we wanted a point that was 10 centimeters north. There's that point P again. Okay. This picture works just as well. Straight up, that way's north. All right. We know that the magnetic field strength is given by mu naught I over 2 pi r. So 4 pi times 10 to the negative 7. I is 25. And then 2 pi. And then r is 10 centimeters, which is 0.10 meters. Okay. That's really just a calculator thing. So we get 5.0 times 10 to the negative 5 Tesla. We do need a direction, okay? Let's think about the direction. I find the directions easier to figure out with this second picture. I'm going to redraw this second picture. If that represents the current and it's coming straight up like this, heading right towards that camera, and this is north, there's our point. I need to know what direction the magnetic field point. Well, if I put my thumb north, if I pretend like I'm grabbing that wire with my hand, I can see that it's going to be counterclockwise circles. So if I draw the magnetic field at that point P, I'm going to need to draw kind of a larger circle here. It's going to look like this. Here's my circle. There it is. It's going around like this. But it's going counterclockwise. At this point, the magnetic field would point that direction. Well, if we're going that north is straight up, the way we've drawn it, then that is to the west. Remember, here's our, this is north, this is south, this is east, this is west. So in this case where we have the current coming straight out, the magnetic field will be circular, but it'll be counterclockwise. At that particular point, the magnetic field points to the west. Now, if you were 10 centimeters below, if you were down here, at that particular point, you can see that the magnetic field, let's draw some arrows here. This is going like this. So at this particular point, if you were right here, the magnetic field points that way. If you happen to be over here, it'd be pointing up. Or if you're over here, it'd be pointing down. Okay? But we were 10 centimeters to the north, so it's pointing west. So the answer to my question is 5.0 times 10 to the negative 5th Tesla to the west. That's, if I remember is correct, that's very, very comparable to the strength of the Earth's magnetic field. Let's look at another problem. This one's also right in your textbook, so you can go read through it again in your textbook. This is example 28-2. In it we have two parallel wires. that are 10 centimeters apart. Carry current in opposite directions. Okay. The first wire carries I1, that's equal to 5 amps out of the page. I'll say out of the board since I'm on a board. And the second one, I2, is 7.0 amps into the board. And they want me to find B. And they want the magnitude and the direction, not just the magnitude. Halfway between the wires. Okay. The picture here is going to be really important. We've got two wires. Their currents in opposite directions. The first one's 5 amps out of the board. So here's I1. It's coming out of the board. I hope you can see that. All right. The other one, 10 centimeters apart over here, is going into the board. That's I2. And it is 7 amps. We want to know what's going on right here in the middle. Okay. It says that they're 10 centimeters apart. So 5 centimeters from this one, 5 centimeters from this one. What's going on? Well, let's get the direction first, because the direction will be helpful. I'm going to pause right here. Hello? Hello? Okay, I'm so sorry about that. I'm afraid it might be important. All right, so if I have current out of the board, I grab this wire, I can see it's going to be counterclockwise. So I'm going to go ahead and draw it right here. That magnetic field line is counterclockwise, which means that right here at this point halfway, it points up. Okay. I'm going to do it for the other one. I'm going to draw it in a different color. If my right hand thumb is into the board, I see that this one has magnetic field lines that are clockwise. But that means that this one at this point also points straight up. That's going to help me solve this problem because I now see that these are going to add together, that both of the magnetic fields are going to add together at that point. They're both pointing straight up. We know magnetic field is a vector, so direction's important. We just used that very first right-hand rule. Out of the board, grab it, counterclockwise. Into the board, clockwise. But that makes them both point the same direction at that spot. Okay? We need to calculate the magnetic field due to the first wire. That's mu naught I over 2 pi r. Mu naught is 4 pi times 10 to the negative 7. For the first one, the current was 5 amps. And the distance here, if they're 10 centimeters apart, this distance right here is 5 centimeters. So that is 0.05 meters. That one came out to be 2.0 times 10 to the negative 5 Tesla. And we know directionally it's pointing straight up. I have to do the exact same thing for the second one. When I do the second one, it looks exactly the same, mu naught. The only difference with the second one is instead of 5 for I2, if I change this to 2, change this to 2, the second current is 7. So this is going to be a slightly larger, and it is. It comes out to be 2.8 times 10 to the negative 5th Tesla, also straight up. All I have to do to get those is add those together. It's just equal to B1 plus B2, since they do point in the same direction. So it's 4.8 times 10 to the negative 5 Tesla. And again, it will point straight up. So not too bad. We just have to get really good at understanding the direction of those magnetic fields. Okay, that's the end of section 28.1. The second section in the book, section 28-2, deals with the force between two parallel wires. Okay. Well, we know that a wire has a magnetic field. So if we have a second wire, it also has a magnetic field. They're going to interact like two magnets. Two parallel wires each carrying current. Now they don't attract unless they have a current. Will each have a magnetic field. And therefore exert forces on each other. Okay. So if I have one wire and it's got I1 going this way, and then right next to it I have another wire and it's exerting I2 going this way, I know they're going to have forces. Let's look at the magnetic field due to wire 1. Magnetic field due to wire 1, if these two are located at a distance d apart, let's see what the magnetic field of wire 1 is over here at this point. It's going to be mu naught I1, just at any point, 2 pi r. Now, wire 2 feels a force because of this. Wire 2 feels a force that's equal to I, L, B, I2, L2 times B1 sine theta. Now, if we think about the direction, the magnetic field is perpendicular right here. The magnetic field is going into the board. So that's going to be a 90-degree angle from I2. Sine theta is going to be 1. So this is going to simplify to I2, L2. That equals 1, B1. B1 is mu naught I1, 2 pi. Well, the distance between them in this case is going to be D. I'm going to clean that up a little bit. And we see that the force that the second wire has to feel is going to be given to by mu naught I1, I2, L over 2 pi D. Now, Newton's third law says that the force that this second wire feels because of the first wire has to be equal to the force that the first wire feels because of the second wire. That tells me that the first wire is going to feel the same force. So really what we get to is we get just a force in general for either wire, and it's mu naught I1, I2 over L 2 pi D, where D is the distance between them. Okay? This force is going to be attractive if the currents are in the same direction. If we think about it, we could figure that out. If the current's going up here and the magnetic field is into the board here, and I curl it with my fingers up and go into the board, I can see that I2 is being pulled towards I1. I could do the other side if I wanted to, but we can see that. So this is same direction, F is attractive. They'll be pulled towards one another. If they are in opposite directions, then F is repulsive, and they'll push away from each other. Okay. Everybody should have that. So we've got our formula for how that works. Do an example. In your textbook, this is example 28-5, and it's about suspending a wire with a current. Okay, we're going to have two wires. There's one wire. This wire has I1, and it's 8 amps. We have a second wire that is located at a distance 20 centimeters below it. So this distance between these two horizontal wires is 20 centimeters. Okay. The question asks, if the lower wire, let's write this down, the lower wire has a mass of 0.12 grams per meter. It's a pretty thin wire if it's less than a gram per meter. How large must I2 be? That's a set. How large must I2 be so that it doesn't fall due to gravity. Oh, that's an interesting idea. Can the magnetic force between these two support this bottom wire so that it doesn't fall? If I drew a free body diagram, it would look like this. We'd have the weight of the wire, mg, and we'd have the magnetic force. And we'd want those two to be equal. Well, one of the things that I can already tell you is that this current would have to be in the same direction. We would want this lower wire to be attracted to the upper wire. And when the currents are in the same direction, there is an attractive force. Okay? This is really where we want to be thinking. We need the force between those two to equal mg. I'm going to have to erase some stuff so I have enough room, but I want you to, I'll leave that picture. And I'll leave that upper picture. Tell you what, I'm going to move that picture, maybe. We know that on the second wire, we want this situation. We want the gravitational force to be balanced by the magnetic force. Okay. So we want mg to equal, the magnetic force is mu0, I1, I2, L over 2 pi d. And we're being asked to solve for I2. That's good because that's going to help us out. If I get I2 all by itself, I'm going to get I2 I2 equals mg times 2 pi d over mu0 I1 L. All right. We know the distance between them. We know mu naught, we know I1. What you may not realize you also know is they told us the mass per unit length. They told us that M over L is equal to 0.12 grams per meter. That's fine, except we need that to be in kilograms per meter. So M over L is equal to 0.12 times 10 to the negative 3, times 10. Yeah, 10 to the negative 3 kilograms per meter. Okay. Let's fill in everything we know. The top part, let's just kind of rearrange this. It's 2 pi d. D is 0.20 times g, that's 9.80, times the mass. We're not going to use mass, we're going to use mass per mass divided by L. That mass divided by L is 0.12 times 10 to the negative 3. On the bottom, we're left with mu naught, 4 pi times 10 to the negative 7, and I1, which was 8 amps. So this M over L came out in our formula, and that's what they had given me. They gave us a mass per unit length, but that worked out just fine. We put all this in, and that second current comes out to be about 14.7 amps. We really only have two significant digits, so 15 amps. That's a very light wire, but if it had 15 amps of current flowing through it, it would be the attractive force could suspend it. Would exactly balance its weight. Okay, that's all for the first two sections of the text, 28.1 and 28.2. We're not going to really talk about section 28.3. It's very short. You can read over if you want. The next video is going to talk about section 28.4, which is Ampere's law. That's really an important one. So I will see you hopefully in the next video.